Here we are in Elementary Calculus, Chapter 5, Section 4, and this is an interesting section. This is about sketching curves, and the art of sketching a curve is kind of a dying art because we have graphing calculators and other online utilities that we can simply type our equations into, and voila, we have our graph. But what curve sketching is really good for is getting to know all of the different processes that we have learned thus far and applying them to either generating your own graph, or in the case of the online homework assignment that I'd like to look at with you in this video, the skills that we've learned so far can be brought to bear on the task of identifying which of the given options represents the function that we're being presented with. So let's go in and have a look at some practice problems. And I'm in the way. Let me move me real quick. The different processes that we've looked at thus far go all the way back to college algebra, honestly, or even before that maybe, because some of the maneuvers that we can use, some of our capabilities include finding x and y intercepts, and I'm failing at multitasking right now, obviously. I was not prepared to have me in the way. All right, let's try that. So going all the way back to looking at y-intercepts, and then going as far forward as using the second derivative test. And the other thing that I will show you from the printed notes, or sort of pre-created notes that I normally reference, is this list. So this is a nice to-do list that you can use when you're tasked with either designing your own curve, or not so much designing your own curve, but if you're given a function and you need to draw the curve that corresponds to that function, you can use this checklist, or you can use it in order to help identify the correct one of maybe multiple choice options, multiple choice options. You know what I mean. Pick the right option. You can use this as a guide. So here are some of the things that we're going to just talk about as we look at some of the problems in this homework set. Because really I've already taught you everything that you need to know. So we're just going to talk our way through a couple of problems. So number one, we're recommended to consider the domain of the function and if there are any restrictions. In other words, we want to avoid dividing by 0, taking the square roots of negative numbers, or if we're working with a logarithmic equation, we want to make sure that the argument ends up being a positive number. You can't take the log of a negative number, and you can't take the log of 0. The argument has to end up being positive. So again, our input values can have an effect on the argument of the logarithm function. So be careful there. We can find y-intercepts. We know that we find the y-intercept by plugging in an x value of 0. We can find x-intercepts by setting our original function equal to 0, if that's not too difficult. Sometimes it's a little bit too cumbersome and ends up being a very time-consuming process. Number 3 says that if we're working with a rational function, and a rational function, remember, is a function where you have your variable in the denominator, you might want to identify any vertical asymptotes, and those are going to happen when your denominator ends up equaling 0. So that's really part of that conversation about domain. You could also locate any horizontal asymptotes by taking your x values and sending them off to positive or negative infinity. Remember, you can also determine horizontal asymptotes by comparing the degree of the numerator to the degree of the denominator. If they're the same degree on the top and the bottom of your fraction, then the horizontal asymptote will be the equation y equals and then whatever your leading coefficient in the numerator divided by your leading coefficient in the denominator ends up being. So if you had a 3x squared in the numerator and a 5x squared as your largest degree term in the denominator, then you would have 3 over 5 would be the fraction made of your leading coefficients, and you'd have y equals 3/5 would be your horizontal asymptote. If the degree of the numerator is larger than the denominator, then you will not have a horizontal asymptote. And if the degree of your denominator is larger than y equals 0, the x-axis will be your horizontal asymptote. You could also go so far as to look for slant asymptotes. If the degree of the numerator is 1 larger than the degree of the denominator, if it's reasonable for you to do the long division, the result of the long division process, disregarding the remainder, will be the equation of your slant asymptote. And if you need a refresher on that, there are numerous videos, I'm sure, where you can go and find some information about slant asymptote. And once I have all of my videos time-stamped, you could certainly search my channel and find a segment of one of my videos about slant asymptotes. Number 4 says that we can look at symmetry, and there are a couple of tests that you can do to determine symmetry. Check that out, and if you don't recall those 2 tests, you've got a little review that you can do there. Number 5 brings us current and into this course, finding the first derivative of your function. If you find the first derivative of your function and you set it equal to 0, that's going to help you find some critical points, potentially, where the slope of the tangent line is equal to 0. So that may be a maximum or a minimum. Not always, but it could be a relative max or a relative min. And you should also determine where your first derivative does not exist. That could give you some insight into what your function looks like also. Once you take your x-axis, your number line, and you chop it up into maybe multiple sub-intervals by noting where your first derivative is equal to 0, then you can test some x values in those intervals and determine where your function is increasing and decreasing. Speaking of which, it's not on this list, but if you're working with a polynomial function, then you should be able to investigate end behavior. As your x values get really large in the positive direction, do your y values tend in the positive direction? And as your y, or do they tend in the negative direction, your y values? Consider also sending your x values toward negative infinity and look at what's happening with your y values as your x values get really negative. Number 6 reminds us that we can look at the second derivative and locate some potential inflection points, which is where our concavity is changing. You can locate those by taking your second derivative and setting it equal to 0. If it turns out that your second derivative does not exist at some or for some x values, if it's undefined for some x values, then you may have an inflection point there also. You might want to test the concavity to the left and to the right of those points in order to make sure that you're looking at a successful inflection point where you're changing concavity. And then number 7 is where we really start putting pencil to paper. You're going to plot your intercepts, your critical points, your inflection points, your asymptotes. Being mindful of symmetry, you might get a little twofer on some of those and be able to reflect them over the origin or over the y-axis, and then connect your points with a smooth curve. And then, since we have the ability to do this, you're probably watching this video on a device where you could do or type in whatever your equation is and immediately get some kind of a graph. Now, whether it's a graphing calculator or you're using an online utility like Desmos.com, you will need to be familiar with how to adjust the size of your window in order to get a substantial and usable portion of your graph on the screen. So whether it's a TI grapher or some other kind of graphing calculator, or if you're in Desmos, consider watching some supplemental videos to make sure that you know how to use them well enough to see your entire curve by adjusting the window, as it's called, on the TI grapher. All right, let's go in and take this conversation to some specific questions. This is a homework assignment that I'm going to be giving my students using MyMathLab, which is a Pearson product. So many thanks to them for, I didn't ask them permission, I'll ask them forgiveness, but let's borrow some of their problems that are associated with one of their elementary calculus books and see some problems. This one is asking us to graph this function, which is a third-degree polynomial. This one, this particular function, setting it equal to 0 in order to find x-intercepts might be challenging. All right, so, oh, I haven't taken action in a while. Wow, so pushy. There we go. So maybe that's not the best use of your time, but certainly plugging in an x value of 0 in order to find your y-intercept would be good. Taking the first derivative to see if there are any maximums or minimums that we might want to watch out for. Testing those to see if those potential maximums and minimums are indeed a max or a min. And you could test those x values in your second derivative to check for concavity. So a number of the tools that we just talked about you could use in order to select the correct one of these graphs. Now this is an active homework assignment that I'm giving my students, so I'm not going to be giving out any answers in this conversation, but just talking about some of the general strategies. This function, I don't really like my location in this video. I feel like I'm looking away from the problems. It's kind of strange. Regardless, in this function, one of the things that's really jumping out at me is that I have the variable x in the denominator. And anytime I see x in the denominator, I know that one of the biggest things that I have to watch out for is division by 0. So certainly an x value of 0 needs to be one of the x values to watch out for. That's going to play an integral role in the graphing process. And I would be willing to bet that it's going to result in a vertical asymptote. It also looks like there's a possibility, I'm looking at option B, that looks like it has a slant asymptote. Looking at option C, honestly, C might have 2 slant asymptotes. Option D looks like it has a pretty firm slant asymptote. Even option A, if I can get it visible, might have a couple slant asymptotes. How would I go about determining a slant asymptote for this function? The way that I'm interacting with my iPad, I can't actually draw on the screen at the moment because it's not a PDF, it's just an active web page. But you could work this function and create a common denominator, multiplying the 4x by x over x. So then you'd have 4x squared in the numerator over x in the denominator. Add your two fractions together and you'll have 4x squared plus 12 all over x. And then your numerator, the degree of the numerator is 1 larger than the degree of the denominator, which means you have the opportunity to calculate a slant asymptote. And you can do the division and you would get 4x. You would have a remainder of, in fact, 12 over x, but we would disregard that. And then you could use that slant asymptote to help you choose the correct graph, combined with the vertical asymptote of x equals 0. And then you could still try to calculate some x and y intercepts. That would be helpful. Definitely you can take the first derivative to see where your function is increasing and decreasing. You can take the second derivative to find the intervals on which your function is going to be concave up and concave down. So this function gives you a lot of opportunities to use the different methods that we've been studying so far in this course to help decide which one of these functions is or which one of these graphs is the graph of that function. This one has an x squared plus 9 in the denominator, so there's no danger of division by 0 there because x squared will either be 0 or positive, add 9 to it. It's going to definitely be positive after that, so no danger of division by 0. The degree of your denominator is 1 larger than the degree of the numerator, so that tells you about your horizontal asymptote. And then after that, just by looking at my graphical options, option A has a number of different changes in concavity. Option B also, C, there's a bunch of changes in concavity. So I would say if you took the second derivative of this function, while that might be kind of a pain because you'll have to use the quotient rule a couple of times, you could do it, set it equal to 0. Once you take that fraction and set it equal to 0, you'll be able to disregard the denominator because the only way to make a fraction equal to 0 is for the numerator to equal 0. So you set the numerator, whatever that ends up being, equal to 0, and that might help you find your inflection points where your concavity is changing, and that might help you immediately identify the correct one of these graph options. In the next question, we've got a natural log problem, and we know that the input values for the natural log or any of our logarithms have to be positive, and in this case we're taking the natural log of x. So our input values, our x values, must be positive, which just from the options that I'm looking at on the screen here, option B is not looking very promising because I can't plug in a negative x value into this function. So option B is out. Option A was a contender, C is a contender, D is a contender. But you can see that just by examining domain for this function, we were able to eliminate one of our multiple choice options. We can't plug in a value of 0 for x, so that's not helpful for finding a vertical asymptote, unfortunately. A first derivative and inspecting where your function's increasing and decreasing would be helpful. Option A is concave up everywhere. Option B is concave up everywhere. Option C here is concave down everywhere. And D is concave up. So we already eliminated, what have I done? We've already eliminated option B because we can't use negative x values. But if we start looking at concavity, if it's supposed to be concave up everywhere, then we can eliminate option C. And if it's supposed to be concave down everywhere, C is the answer. So that tool of looking at concavity and using a second derivative could very well seal the deal on selecting the correct answer option for this question. Oh, this is a very strange looking function. We've got some rational exponents. This function would be really easy to find the first and second derivatives. Those both equate to cube roots, so domain isn't so much of an issue. First derivative and examining where you're increasing and decreasing, I think, would be a good idea. These are, where's option A? Option A has like at least 3 x-intercepts, so you could consider setting the function equal to 0. Certainly the origin is going to be one of your intercepts, but I think all of these pass through the origin. But trying to determine if there are some other x-intercepts, it already passes through the origin, so that's your y-intercept also, so that's not super helpful. But I would say looking at increasing and decreasing would be a good idea here. That's just the first derivative, and I know you all know how to do that. In option B, for example, if you take the first derivative and set it equal to 0, it looks like your function should, the first derivative of the function should equal 0 when x equals, I don't know, where do you think that the tangent line is horizontal there? Maybe at 0.5 or something like that. It might end up being decimal. You might have to use a calculator and zoom in on this function or this graph and see if that's a good choice. Option C has a different x value where the slope of the tangent line would be 0. Option A has a couple of different points, if not 3 different points, where the slope of the tangent line should be 0. Option D might have a couple. So just by determining how many different x values will cause your first derivative to equal 0 should help you narrow down your multiple choice options. And then, since this is a pretty straightforward looking function, try the second derivative test. You should be able to find the second derivative very easily, set it equal to 0, and find where you have some changes in concavity. And the last question in this assignment, what kind of a function do we have in number 6? This is a different format. So here, we're being given a laundry list of different characteristics of what the graph of our function should look like. And just by marching through these and continuing to examine the 4 different multiple choice options, you should be able to start crossing them off eventually. Option A says continuous for all real numbers. Well, all of these look continuous. Option B says differentiable everywhere except x equals 3. Let's look at option A. When x is equal to 3, it does look like our curve comes to some kind of a little curved point there. It looks like the top of a mountain, but it looks kind of pointy. So I'd say our function's not differentiable where x equals 3. Option B, also not differentiable where x equals 3 because it comes to a point. It needs to be smooth and continuous. Option C, fail, not smooth where x equals 3. Option D, fail, right? So you're going to have to continue looking through this list of characteristics and examining each one of the graphs, and eventually you'll run into a characteristic or two where you'll get to start crossing out some of your options. Just keep whittling it down until you've got one answer left, all right? This is a really nice chance for you to do a comprehensive review of the things that we've learned so far and apply them to some graphs, which is nice to bring a visual aspect to what we've been working on for so long. So I'm going to leave you to it, and I'll miss you, but I won't see you again until our next chapter. See you there. Thanks.